Hello, my name is James Dienes. I'm a student with Grantham University. Student ID is Golf 000-37574. This is for my final capstone project. I want to discuss purpose and goals of why I chose this project. And what I chose was a bathtub water level alarm. And the reason why I chose that was because my wife and I have run into a problem with filling the tub, and then in the meantime, while it's filling, to go get our son ready for bath time, and then chasing him around the house and getting dinner ready or cleaning up. You just forget about it, and then before you know it, you're like, oh, the water's still running, and it either gets too high and you gotta drain it, etc. So this is hopefully will save me from overfilling the tub and overusing too much water. And that's basically why I chose this for my final project as well. While setting this up, in multi-sim didn't have some of the components that I had picked to do this project. One in particular was the IC chip, the LM1801 chip, which is the basic, the brain of the whole thing. It's the comparator. So it's what is going to compare the inputs for letting me know that when the water touches my leads, it's going to compare and say, hey, they're there, the condition is met, and sound the alarm. So since it wasn't in there, I had to go in and basically create a layout for it, so I can at least put it in multi-sim itself. So it doesn't have any backgrounds for it either. So I can never run multi-sim and get a correct simulation for it. Along with that, I got my breadboard set up. With this simulated breadboard, it was kind of nice to have it there, just to look at it before I did the breadboard. I think it helped out a little, but as you can see, the way it turned out, my layout here I think is a little better than the way I see it on my simulated. So doing a breadboard in real life, I think is a little better for my instance, since a lot of the components are not in the multi-sim system. I ran into a lot of problems during this project. A lot of it was due to the time for me to actually figure out what I wanted to do for the project. That definitely gave me a time constraint. And from there, picking the components was a little easier, less time consuming, but finding them and then pricing them and buying them and shipping them, it was a whole nother ball of wax. It's not as easy as one would normally think of, just, oh, well, we get the components and then, they ship them to us. I get them in 2 to 3 days or 3 to 5 business days and everything's hunky-dory. Well, Now, we had some that I ran into problems where some were available, but yet after I put the order in, they were back ordered, or I wouldn't be able to get them until December. So I had to seek other places in replacement and pay a little extra overnight shipping or something like that to get them here on time. So my lessons learned was definitely to figure out what you want to do for a project before you started it, but as well a lot more time for acquiring your components, getting what you need together before to have more time to ship and lower your budget costs. My budget, I went over by $15, which wasn't too bad, but it was still over my budget of what I had planned. So as it goes for that, my planned schedule was basically to follow the curriculum given to me through Grantham, week by week. Well, mine had took a turn in the first 4 weeks, so my actual plan was basically, how do you say, turned into compressing it, everything I need to do in 4 weeks. So, okay, on with testing. Okay, for my operational tests, I got my ground wire here. And this thing has been running for over 24 hours now too. So I took some tests when I first started it at different points, like between ground and pin 12 of my LM 1801 chip, just to get some standard references to make sure that it's operating correctly. And for what I calculated, my calculated voltages for pin 12 on my LM 1801 chip was 6.62 volts, and what I measured was pretty close to that. I can put my lead on that right now, and it's got 6.60 or 61, which is good. See if I go between, measure the voltages between pins 12 and 9. Yeah, 2.238 volts, which I round to 2.24, which is pretty close to what I calculated. I calculated 2.38 volts. And the first time I measured it, I got 2.25. So now it's, after 24 hours, it's down at 1/10 of a volt, which is really good. So I got my reference voltages for setting up the biases on my chip. Some reference voltages between ground and pin 2. I'll do ground, and I'm going to do pin 2, and I get 6.76 volts, and the set calculated reference should have been 5.8 volts. I'm getting 6.75, and I believe that, I mean, that's okay. It's takes a little bit more for it to alarm, but I believe the difference in that is due to the 9 volt actually putting out 10.5 volts. So that little higher voltage, it's changing some of the references through the chip. And the reference was based off of the data sheet for the LM1801. And like I've done before, even after 24 hours, the reference voltage is still at 6.76 volts. That is a great, or a very nice thing I liked about this chip when I found it. It's very efficient. The standby mode puts out nano amps, so it uses hardly any power at all. And 9 volt supposedly supposed to last a year. So in standby while it's waiting, you can leave it plugged in if you want, and you don't have to worry about it being dead the next day. But when it does go off, it'll go up to 3 milliamps or so, and I currently can't measure the amperage rating because my meter is not working correctly, so I can only do voltages. See, to actually tell if this is working correctly, I will check my sensing inputs and outputs from ground. See, my sensing input is pin 4, and on pin 4 right now, at standby it should be 0 volts, and which it is. And sensing, let's see, pin 8 is my output sensor, and right now pin 8 is being held at VCC, or 10.33 volts, and it's basically being held there, so it's got 10 volts on either side of this alarm, so it won't sound. But once the leads touch the water, and this is my simulated bathtub. Once the leads touch the water, the alarm will sound. With that, it basically will put a ground on pin 8, and the voltage will go from pin 4 through the leads into the speaker wire, into the speaker, and then back out into pin 8, into the ground. So the voltages, they'll basically just be driving the speaker or the alarm, so it won't take as much current with that either. See if I can test this. to read about 0.59, 0.6 volts, which is normal for this LM1801 chip because it is ground, but it's two diodes latching a ground to pin 8, so you're still going to get that 0.6 volt drop across the diode for the load, or as a load when it goes to ground. So that's why it still shows 0.6 volts on that instead of 0. Okay. And with that, that concludes my experiment and tells me that it's functioning correctly. When I initially run tests, I ran into a problem with the initial speaker I got. I had plugged in there. When it alarmed, it wouldn't go off. It just beeped once. So I think there was something wrong with this, and I ended up having to go out and buy another speaker as well. So that's some more problems you might run into when you're field testing your circuit, and that's why it's so great to have a breadboard. There could be quite a few ways I could improve this design as well. I could get different speakers for different sounds. You can add multiple chips on this for different sensings. Pins 11 and 10 on here, you can string multiple LM1801 chips in parallel to it, and if one goes off, it'll set them all off. So this is a really great chip. You can connect up actuators to actually shut off the water for the tub if you wanted. Since this was mainly a residential and temporary, sound was good enough for me. But I mean, possibilities are limitless really with this. I mean, if you get actuators and amplifiers put in there, you can do just about anything with this. It's good for possibly another way would be a good way to possibly use surface mount components. They would be smaller. You could make it into a tighter little chip pattern, but yet you might run into the problem of external noise or heating issues more. This is pretty stable with half watt resistors and components. Everything's well within the operating voltages, so this thing's been running for over 24 hours and is stone cold solid. Can't get better. And that concludes my presentation for my final project.